Yeah, again, I'm Andrew Wilcoski. I work here at Colorado in LASP. So welcome to Colorado. And first, I'll just give you a quick motivation slide about what pits are and why we care about them. So pits are collapse features. So someplace where the surface has collapsed into some subsurface void. And they're typically characterized by steep walls, maybe connected to things like caves, overhangs, think like skylight into a lava tube sort of thing. This image on the right shows you a bunch of different examples of pits that have been observed on the lunar surface. And you can see we have everything from these nice cylindrical features to these kind of more narrow fracture features. And all of these features have been discussed as potential targets for human and robotic exploration for a number of different reasons. They kind of provide a unique lens into the subsurface of the moon. And also they've been discussed as places you could potentially store ice and potentially protect it from destructive processes like micrometeorite bombardment. And that's because at high latitudes, these features tend to become very effective permanently shadowed regions, or PSRs. And that's really because of their steep walled nature. As many of us are familiar with, PSRs, some of them can be cold enough to allow water ice to be thermally stable on billion-year timescales. So if volatiles existed in these pit and cave environments, it would have a lot of interesting implications for the history of volatiles on the moon, as well as potential resource utilization aspects. So with this work, we really wanted to ask kind of two main questions. The first is, how does pit temperature vary with latitude and geometry? So let's characterize the thermal environments of these spaces. And then the second that kind of piggybacks off the first is, how do pit temperature and geometry end up affecting volatile stability? So should we expect to see ice in these features? Our approach to answering those questions was a modeling one. So we created and validated this 3D thermal model. The model takes as an input a 3D triangular mesh of an arbitrary shape, and then it calculates 3D radiative transfer, 1D heat conduction, shadow casting, insolation at any latitude. So we can create a surface, put it wherever we want on the moon, and see how hot it is. We can generate various input surfaces based on this survey of pits done by Wagner and Robinson in 2014. And we've also created a volatile transport model to model the movement of volatiles within these environments and the stability of volatiles therein. In this talk, in the interest of time, I'm not going to talk too much about the volatile transport model, but that will be in the paper, which should hopefully be submitted soon. So I can show you a couple examples of some different pit geometries that we can plug into this model. So in the upper left there, you can see just a cylindrical pit with an attached cave coming off to the upper right there. The upper right image shows you just kind of narrow fracture. The two images on the bottom are actually showing you the same geometry. So this is that same cylindrical pit with an attached cave, but now I put it in the middle of a big old crater. The image in the bottom left is showing you kind of top down looking into that crater. The image on the bottom right is actually now we're underground and we're looking up at this crater from underneath, so we can see that cave system better. I can show you what this model outputs now. So these are some model results. And this is the cylindrical pit with a cave over the course of a lunar day. You can see the sun rises. The hottest facets are the ones that are seeing direct sunlight. Because this is at such a high latitude, most of this feature stays shadowed the whole time. And a couple important things to note here. The shadowed facets, the dominant source of energy for all of these facets is infrared emission. So it's re-radiated infrared. And you'll notice that means that all the shadow facets tend to have pretty uniform temperatures at any particular time. These things are steep walled, they're really enclosed, so all these facets are just trading energy among themselves. I can show you what the variation in some geometries does to the temperatures of these things. So this plot is showing you the mean temperature within one of 4 different geometries over the course of a lunar day. The purple is for that cylindrical pit. The blue is for that cave attached to the cylindrical pit. The green is an east-west oriented fracture, and the yellow is a north-south oriented fracture. And the shaded regions are just showing you the max and min temperatures at any particular time in one of those features. A couple things to notice here. One, the east-west fracture ends up having the coldest daytime temperatures, colder than the cave. A cave and the east-west fracture end up having the most stable temperatures, so the least variation between nighttime and daytime. And the cylindrical pit ends up having the most efficient nighttime cooling, and it also gets the hottest during the day. The reason it's able to cool so efficiently at night is because a lot of the facets in the cylindrical pit see more of the sky and therefore can radiate energy away and cool off. That's not the same. The same can't be said for the cave, and it can be said less so for the east-west fracture, this narrow feature. Important thing to note here is that all of these geometries remain above 110 Kelvin during the daytime. That's important because we use that temperature as this kind of benchmark for water ice stability. So we say below 110 Kelvin, water ice is stable on billion-year timescales. Above that, not so much. So what this is telling you is that these environments are not necessarily ideal for water ice stability. You might not expect to find water ice within these environments. Now, there's a couple things you can do to geometry to kind of change that conclusion, and I'll show you an example of that right now. So again, we're looking at that pit cave system that I've now put in this crater. So the left plot is looking down into the crater. The right plot is we're underground looking up. And this crater is at a high enough latitude that it actually has a permanently shadowed region within it. And so that pit system is within that permanently shadowed region, and we call that a doubly shadowed region. So now the only energy that's getting into this pit system is from reflected off of that crater rim and the infrared coming from the rest of the crater. And what we find is double shadowing makes pits and caves significantly colder. So the dotted lines here are showing you mean temperatures for the not doubly shadowed case of that pit cave geometry. The solid lines showing you the doubly shadowed case. You can see they're significantly colder. You're still getting above temperatures of 110 Kelvin in this particular instance. But what this is showing you is basically that in order to have these pit and cave features be cold enough to, support water ice stability over really long timescales, you need to have kind of particular geometries. So just a couple conclusions I'll make are first, the steep wall geometry leads to really efficient infrared multiple scattering. So you end up with really the most important energy source here for all of these features is infrared. Cave temperatures end up being stable in time and uniform in space, and we're finding that these caves are approaching black body behavior. The pits and caves outside of PSRs in our modeling experience tend to be too warm to really host water ice over long periods of time. However, things like doubly shadowed pits and caves have colder, more stable temperatures. And so volatile trapping may occur in these kind of specific geometry cases. So these are just some kind of important things to take into account if you're, especially if you're planning a mission to one of these pits or cave environments and you're wondering whether or not you're going to encounter volatiles. So thank you.
Great. Questions for the speaker? Norbert?
Nothing online?
Okay, I think we've got a couple in the room. Lizeth.
Yeah, Lizeth Pagania, APL. Andrew, I was wondering if you've looked at how your results would change with the size of the pit and if you would expect it to change even.
Great question. We've looked at that a little bit. That's kind of a project I'm wrapping up right now. But ultimately, what we're seeing is because the geometries are the same, even though it's a larger geometry, they still approach black body behavior, especially if you have like a cave, even if it's like a larger cave. Yeah.
Thank you.
Yeah.
Go ahead.
Yep, Ben Bussey, APL. I was just wondering, even when it gets warmer than 110 Kelvin and they're bouncing around, it's still a very small aperture to lose volatiles. Have you done the modeling to look at what the rate of loss would be and what kind of incoming mechanism would you have to be able to counter that?
Yeah, so we that's exactly what we're doing with the volatile transport model. We have like, it's essentially a ballistic model kind of thing. And we're finding that escape from these features is still quite efficient. But in the cases like you have with the doubly shadowed case, stability you can trap volatiles for a much longer period of time. And part of that is that kind of smaller aperture effect.
Yeah. There is a question online by Michael Boston. How deep into the cave before you approach the geothermal dominated temperatures?
I'm sorry, I didn't quite hear that.
How deep into the cave until you approach a geothermal dominated temperatures?
That's a great question, Norbert. What we're finding is that you'd have to go exceptionally deep into the cave. I think that's farther than we've modeled at this point. I think the key there is one of the assumptions we're making, and something that's been looked at by Tyler Horvath in his recent paper, is that the regolith over these cave features is incredibly insulating. So you lose very little energy like via conduction through the surface. So essentially, the only way to lose energy from once it gets into this cave is out of the entrance to the cave. And what that means is that you, instead of approaching geothermal temperatures, you essentially just approach a black body temperature as you move farther back in the cave. The temperatures just gets more and more stable.